Alright, welcome to today's lesson on ASCII codes. Now if you remember from previous lessons, all information in a computer is stored as a series of binary digits that are either 1 in the on position or 0 in the off position. That means that everything you could possibly imagine being on a computer, videos, pictures, text, numbers, everything is going to be stored as a 0 and a 1 on your computer. In the last couple of days we've looked at how to take number values 1, 2, 3, 4, 5, 800, whatever, convert it into its binary equivalent and store it on a computer. But how are we going to do that with words? How can we represent text by only using ones and zeros? Well, the answer to that question is the topic of today's lesson, ASCII codes. Now the ASCII code is short for the American Standard Code for Information Interchange. It was created in 1963 to replace an older version of the same idea that was a little bit more complex to use. And the way the ASCII code is going to work, it's going to take a word and it's going to store it in consecutive bytes of memory, or in this case 40 consecutive bits for the word hello, so we can store it and get access to it later. Let's see how this works. Words can be represented in binary by creating a code to represent each individual letter. But how many codes would you have to in order to be able to store all the possible letters that we'd want to work with? Well, think about it. You have to have 26 letters in the alphabet. You have to have 26 capital letters in the alphabet. You have to have all your numbers 0 through 9. You have to have all the symbols that are above those numbers in your keyboard. And then 20 plus other punctuation miscellaneous symbols like comma, periods, slashes, quotations, and so on. You add those up, you get a total of 94 plus codes that are required to store your numbers. So how many bits of information would be needed to hold all 94 different possible codes? The answer? 7. Because 7 would allow you to have 128 different codes in base 10. Right? Since computers work better in multiples of 2, a code was created that stores these code symbols for our letters and numbers using 8 bits of data. Right? We're going to use 1 byte or 8 bits, or if you want to break it down, 2 nibbles of 4 bits each. So here's what the ASCII code table looks like. And you can see here all the different representations of all the characters that we need to work with. So what I can do is I can say, oh, I need a capital H. Well, that's going to be the code 72. Code 96 is an apostrophe. Code 114 is a lowercase r. So now we're going to show you how to convert our text into the binary values so that we can store it on our computer. And it's really quite easy. We're going to start by writing the word hello in binary. First, you have to identify the ASCII codes that we need to convert. So capital H was 72. Little e is 101, little l is 108, and little o is 111. Once we have the decimal values, we can convert that into its binary equivalent using the lessons that we talked about in the previous couple of days. So if we do that, we end up with these values. Then all you have to do is write each letter one after the other to form the entire word. So this says H-E-L-L-O. So in binary, I have just said hello to you. Now we can do the same thing in the reverse. We can take the binary code and convert it back into text so we could display it on a screen so you could see it. So now I have another code right here. Same thing. What we're going to do is convert it into 8-bit segments. So you see I put a little space here so it's easier to see. Then you're going to convert each of those decimal values into their binary equivalents. When we do that, we get these results. Hopefully you got the same ones. All you then need to do is look up those values on the ASCII table to figure out what our word is. So if I go through and do this, we can see 65. I'll make this a little bit smaller so we can see it, hopefully. This is going to let me do this. Okay, it's mildly irritating, but let's see. 65 is 65, capital A. 83 is S. 67 is C, so ASC. 73 is I, ASCII. So this would convert out to ASCII. That's it. That's all we have to learn for today. We'll see you in class tomorrow where we can practice what we've learned.